We can use the periodic table for more than simply determining the name of elements, their atomic masses, or finding ground state electron configurations. In fact, there's a good many trends that any good chemist needs to be aware of. Most of the trends go diagonally across the periodic table, being either highest or lowest near francium at the bottom left, or highest/lowest near fluorine in the top right. Some of the trends do apply to the noble gases. Others involve the way that the chemicals react, and since they just don't, kind of ignore the noble gases for these trends. Once again, it does vary depending on what's going on. So a few of the trends are going to be things such as atomic radius. This has two features taking place. First, as you go down the periodic table, you're adding more shells. This is like adding layers to the onion. Of course, they get larger. Surprise! What is, however, actually surprising is as you go across the periodic table. They get smaller. You think, hey, there's more electrons in fluorine than there is in lithium. Shouldn't it be bigger? Well, there's a thing known as effective nuclear charge. And this is actually playing a role when you're going across the periods. So if you look at an atom, you have protons in the middle, once again the nucleus, and they are pulling on the electrons. Electrons that are in the valence shell experience the protons, but those are being filtered out a little bit by electrons in the core. So if I have, say, fluorine, there are 2 electrons in the core of fluorine, or those 1s2 orbitals, that are shielding the electrons in the valence shell at least a little bit. The electrons in the valence shell don't really shield each other all that much, and so don't really play a role in this to any large degree. Now, fluorine has a good deal more protons than that of lithium. But since the electrons aren't doing much in the way of shielding each other, each electron feels the force of all of those extra protons, having a higher effective charge. Yay! So in general, the farther you go right along a period, the smaller your atom is going to be, as the greater effective nuclear charge of the core is able to pull it tighter and tighter. Now, that greater effective nuclear charge can play a couple of interesting roles. Remember, it's going to go down as you add layers, so it is of course going to go down as you drop down the periodic table to higher and higher periods. Okay, well, if my effective nuclear charge is high, I'm going to be able to attract electrons. If I'm sharing electrons with another atom in what we call a covalent bond, or actually in a couple of other forms like metallic bonds, then I'm going to be able to hog those electrons, a property known as electronegativity. Atoms like fluorine generally can hold on to their electrons and share somewhat unevenly with other elements. Additionally, it's going to be a lot harder for me to knock off an electron from, say, a fluorine, because it has a strong effective nuclear charge. The amount of energy it takes to take an electron from where it's at, specifically the outermost electrons, from where they're at, and kicking them off of the atom, making a cation, is known as the ionization energy. We usually look at first ionization energy, as is the amount of energy it takes to remove the first electron. Of course, there is second, third, fourth, fifth, however many you want to go, ionization energies. Typically, these will jump greatly once you have removed all of the electrons from a shell and you're now trying to remove what used to be a core electron. But, of course, that depends on which atom you're on as to how many you need to do that. Fluorine's got a lot of electrons in its outermost shell. Things like, say, sodium only has 1. So it's easy to knock off the first one from sodium. The second one, that's a doozy. The lower the effective nuclear charge, the lower the amount of energy it takes to knock off that electron. So, elements like francium, down on the bottom right or bottom left, are going to require the least amount of energy to remove an electron. These typically form cations, no surprisingly. Those on the top right, which takes a lot of energy to remove an electron and actually could really attach a few more, tend to form anions. That's again, high effective nuclear charge. You can also look at atoms and discuss metallic character. This is how well they share electrons in kind of a communal sea, or what we call an electron sea. Those with a relatively low effective nuclear charge are able to share somewhat equitably in kind of a great electron commune. And these become very metallic. All of these interesting interactions between electrons and nucleuses allow for some interesting interactions between light, and thus, hey, metals tend to be shiny. And really, the left two-thirds of the periodic table are what we typically call metals, those with relatively high metallic character. Additionally, metallic bonds where you form these electron seas are going to be very good at conducting electricity and heat, as well as rearranging the atoms, making metals, or things with high metallic character, very ductile, or able to be pulled into wires, and malleable, beat into sheets. And those are actually two different properties. So you can have, be more ductile than you would be malleable kind of scenario, or vice versa. Elements with low metallic character tend to share much more discretely and tend to have much simpler electronic structures. Therefore, they tend not to interact with light quite so universally and tend to be fairly dull and may very well have a color to them because they interact with some wavelengths of light differently than others. Additionally, they're going to find it difficult to rearrange their atoms, so they tend to be brittle instead of malleable and ductile. Likewise, they tend to be good insulators, since you have to move the whole atom or whole molecule in order to do that, and you will find most of your gases in this area. You will also note that there are those elements that, once again, this is a continuum, that don't really fit into either of the two generally broad viewed categories of metal and non-metal. These are the metalloids. There's a relatively small number of them in between the metals and non-metals, and these will have rather interesting properties of both metals and non-metals. And especially important is that with doping, or the addition of other elements to a crystal structure, not involving cheating at sports, but changing the crystal structure with adding a few other things, you can make a bunch of, say, silicon atoms lean one way or the other, which is the core of microcircuitry. You'll also notice that while the trend doesn't hold true for all atoms, you tend to be a little bit more extreme in your chemical reactivity as you go towards either one of the two corners that the aforementionedly discussed. When it comes to the aforementioned properties, things of course change when you're no longer dealing with atoms, and instead you're dealing with ions. As far as size goes, cations typically are always smaller than their respective anion because they have lost at least one electron. Therefore, they're going to probably be a tad bit closer, and quite often, cations have lost an entire shell. Their valence shell is simply gone. In that case, they're going to be a good deal smaller than their original atom. Likewise, anions typically are a tad bit bigger. Once again, electrons do provide a tiny amount of shielding next to each other, so that will cause things to expand out just a little bit, because there's, once again, more electrons than there are protons. So while the effective nuclear charge doesn't change much, it will be changed a little bit. There's always an interesting example when looking at atoms that have the same electron configuration but a different sized nucleus, what we call isoelectronic. Iso means same, electronic, electronic structure. So if we were to look at fluorine minus, neon, and sodium plus, then we would see an interesting trend. Sodium plus would be the smallest of the lot. It has the highest effective nuclear charge, it has the most protons, and fluorine minus would be the largest of the lot. It has the least number of protons, even though they all have the same number of electrons. Of course, their reactivity is going to be somewhat different, but at this point, the fact that they're ions tends to overshadow most of the other chemical reactivity properties. With that said, have a wonderful day, and I'll see you next time.